In the first session, we're going to actually talk a little bit about combustion and its application. Then we're going to talk about fields and subsection related to combustion CFD simulation. Afterwards, we're going to talk about physics of combustion and different models and categories that exist for combustion. And finally, we will give you a summary of different models implemented in the Fluent software, which would come to help when simulating a combustion process. The most important question that we should first answer is that what is combustion? Combustion is a type of chemical process in which an oxidizer and a substance react at high rate, producing extreme heat and sometimes light along with other chemically changed products. In other words, combustion is the process of setting fire to a fuel in a controlled manner. In this process, a complex sequence of chemical reactions occur between fuel and oxidizer, accompanied by liberation of heat and light. The three main components of a combustion process must always be present in order for the combustion process to continue. These components are fuel, oxygen, or any other oxidizer, and heat or ignition. If any of these components are missing or their proportion relative to each other was not right, the combustion process will stop taking place. Generally, combustion can be categorized into two groups, complete and incomplete. In complete combustion, the reactant burns in oxygen and produces a limited number of products. For instance, when a hydrocarbon burns in oxygen, the reaction will primarily yield carbon dioxide and water vapor. When elements are burned, the products are primarily the most common oxides. Carbon will yield carbon dioxide, or sulfur will yield sulfur dioxide, and so on. Incomplete combustion will occur when there is not enough oxygen to allow the fuel to react completely to produce carbon dioxide and water vapor. It also happens when the combustion is quenched by a heat sink, such as a solid surface or flame trap. As in this case, with complete combustion, water is produced by incomplete combustion. However, carbon and carbon monoxide and hydroxide are produced instead of carbon dioxide. Carbon monoxide is one of the products from incomplete combustion. Carbon is released in the normal incomplete combustion reaction, forming soot and dust. Since carbon monoxide is a poisonous gas, complete combustion is preferable. As carbon monoxide may also lead to respiratory troubles when breathed, since it takes the place of oxygen and combines with hemoglobin. ANSYS Fluent contains models which are applicable to a wide range of homogeneous and heterogeneous reacting flows. Nowadays, humankind exploit the combustion process due to the right amount of heat energy release it has compared to most of other type of fuels. Examples of such reacting flows are listed here, which are furnaces, boilers, gas turbines, and so on. But they are not confined to the mentioned items here. Regarding the importance and reason behind combustion CFD modeling, as you all know, fossil fuels are the biggest human resource for generating energy and heat for other processes. While the fabrication and design consideration must always be a paramount for such applications due to the high temperatures, the biggest problem in the way of combustion using fossil fuels is its pollution generation. If measures such as correct proportion of fuel, air, temperature increase constraint, and so many more items are not taken into account. One of the greatest helps of combustion CFD modeling is that it can give us huge amount of information about the species concentration and their distribution, along with predicting pollution generation. As you all know, when we speak about combustion, there are always other aspects to it other than heat or light or pollution. For instance, for extreme combustion cases where the generated heat is considerably higher than normal combustions, the radiative heat transfer mode on top of convective heat transfer should be modeled. Or for most combustion applications in real world, the fuel and oxidizer are not mixed at molecular level and the fuel is injected in spray form such as in the cylinder of IC engines. However, the most important aspect to correctly modeling the combustion is to consider the turbulence chemistry interaction. There are always two sides to a combustion process, the chemical kinetics and turbulence effects, which mutually affect each other. Another type of classification for combustion process is how the fuel and oxidizer are mixed. Generally, flames can be categorized into three groups of non-premixed, premixed, and partially premixed. In the non-premixed flames, as its name speaks for itself, the fuel and oxidizer are not mixed initially, and fuel or reactants enter the flame sheet due to convective or diffusive effects. In the premixed, the fuel and oxidizer are mixed with each other at molecular level, and flame front propagates into the fuel as it burns. And the final group is the partially premixed flames, where a combination of non-premixed and premixed system exists. Now, regarding the existing models and approaches for modeling combustion in Fluent, there are three main groups of non-premixed, premixed, and partially premixed. The non-premixed combustion can be modeled through, first, the species transport submodel, which is capable of solving both types of combustion, meaning the non and premixed. This submodel solves the conservation equation for multiple component species and for each of them. The user may specify multiple chemical reactions to model simultaneously, with reactions occurring either in the bulk flow, at wall or particle surfaces, or in the porous region. But the limitation is that inside any combustion process, there may be tens to hundreds participating species, which we may only consider a handful of them using this approach. The second submodel which can be used in this category is the non-premixed submodel. In this submodel, transport equations are written and solved for mixture fractions rather than for individual species. Species concentrations are calculated from the resulting mixture fraction field. The mixture fractions approach assumes that you are modeling a combusting system with discrete fuel and oxidizer inlets. The non-premixed combustion model rests on the assumption that the instantaneous thermochemical state of a fluid can be related to a conserved scalar quantity, the mixture fraction. Also, it assumes that the mixing timescale is lesser than the chemical timescale. Next, regarding the premixed combustion approach, which can be modeled using two submodels of a species transport and premixed submodels again, the species transport submodel was explained earlier. But regarding the premixed submodel, in this submodel, fuel and oxidizer are mixed at the molecular level prior to ignition. Combustion occurs as a flame front propagates into the unburned reactants. Examples of premixed combustion include aspirated internal combustion engines, lean premixed gas turbine combustors, and gas leak explosions, and so on. Also, this submodel uses a simplified method known as progress variable to solve conservation equation. And finally, for the partially premixed combustion model, this method is a combination of non-premixed and premixed methods in which mixture fraction and progress variable theories are both considered. And finally, as shown here, we have classified the main approaches present in Fluent for combustion modeling in terms of fast or finite rate chemistry. As was mentioned before, for the cases where the turbulence effects are dominant, the fast rate chemistry must be used, while in the cases where the chemical kinetics are far more important and have a greater effect on the combustion process, approaches using finite rate chemistry are to be used. And of course, to understand which approach and which chemistry should be used, we must first calculate the Dom-Kohler number, which is the ratio between mixing timescale and Arrhenius rate timescale.
To benefit from Mr. CFD services, including simulation, consultation, and training, contact our experts via info@mrcfd.com or visit our website www.mrcfd.com.